Continuing on with our discussion about Java parallel streams internals, let's give a quick overview of the splitting, combining, and pooling steps, which are just basically the split, apply, combine stuff we talked about before. But now we're going to talk more specifically about how these things are done. And again, always keep in mind what you can and can't change. And here we're going to talk about the things that you can change. So by default, if you use a parallel stream out of the box and don't do anything custom or anything that's tailored for your environment, the splitting, combining, and pooling mechanisms are invisible. They're like a hooded ninja. You don't see them. They work out of the box. Why is it that way? Well, for one thing, as I've talked about a couple times, all Java collections, which are often, though not always, the source of streams, have predefined splitterators that create parallel streams from whatever type of collection you're dealing with, an array list, a linked list, a tree set, and so on and so forth. Now, it turns out that the choice of collection makes a big difference, and we'll take a look at that later if we have time. But everybody has a way to turn themselves into a sequential or a parallel stream if they're a Java collection. And how do they have those things? Well, if you take a look at the collection interface, which is what you get out of the box, because that's the root of all collections, there are some methods defined here. And with Java 8 and henceforth, you can have these things called default methods. And a default method is a method in an interface that has a default implementation. Now, you can always override it if you want, and some of these things are overridden. But out of the box, you get these default behaviors, which is very convenient. And here's some things you get. You get this thing called a splitterator, which will take the object and then call the generic splitterator method on it. If a collection doesn't like the default, it can customize it and override it using good old object-oriented programming 101 techniques of subclassing, overriding behaviors and base methods and so on from superclasses. And we won't really look at the implementation of this, but we will perhaps talk later about some common splitterators for things like linked lists and array lists. Now, there's also these factory methods that make streams. Here's the parallel stream factory method. And this goes ahead and uses the stream support.stream factory method, taking the splitterator for whatever type of collection this thing is, and then telling it, I want this to be a parallel stream. And that's what happens when the true method is given, or the true flag is given here as opposed to false. If we had false, it would make a sequential stream. And that's what the stream factory method does. It just says false. So that's how the collections work. And surprise, surprise, you can make your own collections and define your own splitterators, and then parallel streams and sequential streams will automatically be created for you by using these factory methods that come out of the collection's default factory methods. Java also predefines a bunch of collector factory methods in the collectors utility class. And we've seen a bunch of these so far, and you'll get a chance, hopefully, to play with some more. So collectors has a whole slew of these things. For example, we just talked about the teen collector, which came with Java 12. That's an example of a factory method that creates a teen collector in the collectors utility class. By the way, a utility class in Java is just a class that has only static methods and either no data or only static data. It typically has a private constructor, and it's final, so you can't subclass it. It's basically a namespace for functions, if you will. And here are some of the popular factory methods: toList, which turns the stream into a list, an array list; toSet, which turns the stream into a set, and I think it's a hash set by default. And these are all non-concurrent collectors that are created out of the box. I think there's one or two concurrent collectors that can be created as well. I think there's like two concurrent map, perhaps, but most of them are going to be non-concurrent collectors. And then finally, and this is the really interesting part, this is the part where we'll spend time on the other ones too, but you can, the common fork join pool is the means by which the streams framework runs these intermediate operations on chunks of data in parallel. So this is a pool of threads, typically sized to the number of cores, -1. We'll talk why there's -1 later. And that's where all these things run after they've been turned into chunks. So you can customize any of these things you want. The stuff we just looked at is what comes out of the box. Well, yeah, let me rephrase it. You can customize splitting and combining. It's a little harder to customize the applying, but you can do a little bit. So here's the Splitterator interface. This is what you get out of the box. And this is what all the collections in Java Collections Framework implement. But you can come along and customize them yourself if you don't like the way it works. For example, you might think, gosh, it's overkill to break up, to split an array list into elements of size 1. I want to have them be broken up into elements of size 5. Well, it doesn't do that out of the box, but you could make your own splitterator that would do it that way if you were so inclined. And the try-advanced method is used for both sequential and parallel streams. The try-split method is used for parallel streams to break things up into chunks that are going to be farmed out to threads in the common fork join pool during the apply phase. Likewise, there's also this collector interface, which has a bunch of methods defined on it. And this is what, again, comes out of the box with those predefined collectors that are in the collectors utility class. And you can customize these things if you so choose. Again, I've done this mostly for examples. Most of the time, what you get out of the box works perfectly fine. But it's kind of neat to see how you can do that. And then the third thing you can do, and this is for the apply phase, is you can, to some extent, control the amount of parallelism available for tasks that run in the common fork join pool. So by default, you have the number of cores minus 1 threads in the common fork join pool, which works fine for compute-bound operations. Think about this for a second. We'll talk more about this later, but a compute-bound operation is one where it doesn't, the thread that's running doesn't block on synchronizers or I/O or other things that might take a while to run. So it just runs to completion. And so, for example, computing factorial or the greatest common divisor, those would be examples of compute-bound operations. So if you've got n cores and you have only compute-bound operations, there's really no sense in having more than n threads running, because if you have more than that, those threads aren't going to do anything because all the threads that are running are run to completion operations. So there's no benefit in having more than n threads if you have n cores. However, for I/O-bound operations, where you're waiting for downloading images from a remote server, or you're doing file access or database operations or whatever, rebalancing a B tree, whatever you do that might block, then it does make sense often to have more threads than there are cores. Because when one thread blocks for I/O, either reading or writing, then other threads can run. So there's a benefit to having more threads. And so Java provides this ManagedBlocker mechanism that can be used if you want to take control over the number of threads that are available in the common fork join pool. And the way it works, without going into too much detail, we'll cover this later, is that it allows threads to be created to compensate for blocking threads. So at any given point in time, you may have more threads than there are cores because some of those threads are blocked on I/O operations. But the way that the ManagedBlocker mechanism works in the context of the common fork join pool is that if those threads are created and then they're not used for a period of time, they are reclaimed. They're basically taken away. So things will temporarily grow, and then when the period of bursty operations goes away, then they will shrink back down to the default size, which again is typically number of cores minus 1. So that was the end of the quick overview of splitting, combining, and pooling. The key thing I want you to be aware of here is that lots of stuff comes out of the box, but you can control certain aspects which could be very important when you're trying to optimize your programs.